is part 2 of the momentum impulse video. Okay, in the first part I defined all the terms. Now we're just going to do the problems. So the first one I'm going to do is on page 2. It says to write a formula between the momentum and kinetic energy. Okay, so kinetic energy is 1/2 mass times velocity squared, right? Momentum is mass times velocity. And the momentum is a vector quantity, kinetic energy is not. Okay, so if I want to write a relationship between momentum and Ke and the mass, so I can see that in here there is an m and a v square. So I think if I can multiply this by m and divide by m, I will actually get mv squared. I can take the square to the outside. So that looks like it's 1/2 p squared over m. Right? Another way you could do this is you isolate the v in the P equals mv formula. You substitute it into the kinetic energy formula, and you should get the same answer. So that's going to be an important formula to remember. That's not in your formula sheet, so you have to either come up with it or memorize it. Okay. The concept check, I guess, we'll leave for class. All right, so let's look at some of these problems here. Okay, a lot of these are extremely simple. Okay. All right, so the first one is a 2,000 kilogram truck rolling at 4 meters per second is near a 500 kilogram car going at 18 meters per second. So if you want to find the momentum of the truck, you just basically take momentum of the truck, I guess PT is the mass of the truck times the velocity of the truck, and you can multiply the 2,000 by the 4. Same thing for the car, you do 500 times 18. Which one would be harder to stop? It will be the one that's going to have more quantity of motion, in other words, more momentum. So you have to do the multiplication and see which one is bigger. So according to what I have here, the car has 9,000 kilograms meters per second. The truck has only 8,000. So it's going to be harder to stop the car. Okay. Second question is, a 1,200 kilogram car accelerates from 5 meters per second to 15 meters per second. What is the change in its momentum? All right, so the change in momentum is basically your final momentum minus your initial momentum. So your final momentum is 1,200, or you can just do it m delta v. It's really up to you. I'll leave that up to you. Times 15 minus 1,200 times 5. So that should be 12,000. 12,000 kilograms meters per second. Okay? Because the mass is in kilograms and the velocity is in meters per second. Number 3, a pool ball of mass 0.5 kilograms is hit and comes to a stop on the pool table. If its change in momentum is negative 12 kilograms meters per second, what was the ball's initial velocity? So change in momentum equals m final velocity minus the initial velocity. Remember the formulas I told you to kind of like put next to each other instead of looking at them separately. So impulse is change in momentum or causes the change in momentum, and that's going to be, and this here, J is Ft, and delta P is m delta V, and delta V is m final velocity minus the initial velocity. I highly recommend that you write them next to each other, and then you decide what part of that big equation you're going to use, or equations. Okay, okay, so here I think is just, you say negative 12 here equals half times, comes to a stop, 0 minus the initial velocity, and it looks like it's going to be 24, positive 24 meters per second. Number 4, while sliding across the ice, a hockey puck traveling at 23 meters per second experiences a change in momentum of negative 10, which means it's got to be slowing down because the change in momentum is negative. And it comes to rest. As it comes to rest, what was the mass of the puck? So delta P equals m delta V. Okay, so you have this as negative 10. The mass is the unknown. we come into a stop. It says here it comes to rest, minus the initial velocity, which is 23, and you get what you get. So the answer is 0.43 kilograms. Now I talked about this impulse. We did some demonstrations in class. So we're just going to go right to the problems. Okay. Jack pulled a pail of water with a force of 7 newtons for 2 seconds. What's the impulse? So impulse is just force times time, based on what I have here. So it's just going to be 14 newtons times seconds, not per seconds. Okay. Jill will have to pull the same pail as Jack. Jill only pulls with a force of 3.5 newtons. How long will she have to pull to produce the same impulse? Now, impulse is Ft. So if the impulse stays constant, the F and the T are inversely related. So she's only going to apply half the force. She needs twice the time. Or you can just do the math. You can do 14 equals 3.5 times time, and you should come up with 4 seconds. Little Joe pulls the same pail with a force of 10 newtons. How long will you have to pull to produce the same impulse? Again, you can put 14 equals 10 times t. It's probably easier than doing proportions. Number 6, a Honda engine pushes with a force of 250 newtons for 6 seconds to speed up the car. What's the impulse? You just have to multiply those two. So a lot of these are easy actually. A Porsche engine pushes with the same impulse as the Honda, except in a shorter time. Half a second. What force must the engine exert? So if the impulse is the same, we can just do proportions here, right? 1.5 seconds is only 25% of 6 seconds, so it's a quarter. So which means the force has to be 4 times as much. So instead of 250 for the Honda, the Porsche should exert 1,000 newtons. Okay, or you can just use the formula. The derivation of the equation, this was done in the last video. Okay, part 1. All right, number 8. The graph shows the force on an object of mass uppercase M as a function of time. For the time interval 0 to 4 seconds, the total change in momentum is, all right, so I know that if I have a force time graph, the area between the curve and the time axis represents impulse. So this area here looks like it's 20, positive 20, and this area here looks like it's negative 20. So basically there is no change in momentum here. So it's basically 0. Okay. Because impulse is change in momentum. That's actually what causes the momentum to change. Okay. Now let's look at some concepts here. It's not the fall that kills you, it's the sudden stop. Okay? Okay, so and the reason for that is because the time it takes to come to a stop. Actually, I'm going to skip some of these concepts. You're going to have to try this on your own. I'm going to go right to some of the problems. So I'm going to go to 17. Right? A 20 Newton force directed to the west is applied to a 12 kilogram cart moving east at 2 meters per second. So the force is going this way, and the object is going to the right, the other way. So I'm going to look at right as positive and or east as positive and west as negative. What's the final velocity of the cart if the force acted for 3 seconds? All right. So this is what I'm going to try to do. I'm going to say the initial momentum, okay, plus any impulse, and this is a vector quantity, but since this is one-dimensional, we can get rid of the vector symbol, right? Equals final momentum. And that pretty much comes from this first part here. Impulse equals change in momentum. In other words, impulse is final momentum minus initial momentum. If I add the initial momentum to both sides, I get initial momentum plus impulse equals final momentum. This is going to be very useful. It's going to be very useful to look at it this way sometimes, especially when we do the bar charts for momentum. Okay. So let's see what we have. So going to the right, so that's going to be the mass, which is 12 times 2. Okay. The impulse exerted on this is going the other way, the opposite way. Okay. So this is going to be minus force of 20 times 3, that's my impulse, equals final momentum, which is 12 times the final velocity. Now, if you put a plus here, right, you will get velocity that's higher, which doesn't make sense. Okay. All right. Another way you could do this, you can just say J is m Vf minus Vi, and you should get the same answer. Okay. The only thing you have to be careful with, you have to make this a negative, because the force is opposing the motion. Okay. All right. So a 70 kilogram parachutist jumps from a 300-meter elevation. The chute fails. Okay, so now they're going to go into almost free fall. Okay, if he comes to a stop in 0.5 seconds, now keep in mind that 0.5 seconds is not the time that they spend in the air. 0.5 seconds is just the time it takes them to go from whatever speed they're going to hit the ground with to 0. Okay, how much of a force does he experience? Okay. Now here, I think we have to first figure out, so I'm going to we first have to figure out with what speed they're going to hit the ground. Okay. First, so I think we can do kinematics, we can do conservation of energy, we can do whatever you want. So they are here, that's when the chute fails. This is the ground. Now when they hit the ground, it's going to take half a second to come to a stop. So I think what I need to do, I need to figure out with what speed they're going to hit, okay, and then do the collision all the way down here, because the force is only exerted when they hit the ground. All right, so the height is 300 meters, okay, and that's it. So I'm going to do conservation of energy, assuming that there is no air drag, right? So it's going to be mgh equals half mv squared. My initial state is the moment the chute fails, and my final state is the moment they're going to hit the ground. So up here at the initial state, I only have gravitational potential energy, assuming I choose the ground as the reference. And at the bottom, I'm only going to have kinetic. So we don't care about the mass. That's going to come in later. So this is going to be 10 times 300 equals half of v squared. Now, if you do the math, you should get a velocity equal to 77.46. Now, this could be plus or minus 77.46, but this is what I'm going to do. I'm going to choose down as positive, right? Okay, it's just a choice. If I choose up as positive, then I'll have to make that negative. So I'm going to keep it as positive, okay? And when I finish, the value, the force should have a negative in front of it, because the force will be pointing the opposite direction. Okay. So now let's do the impulse momentum theorem when they hit the ground. So it's Ft equals m delta v, or final velocity minus initial velocity. So we're looking for the force. It takes half a second to go from 77.46 meters per second to rest, equals the mass of the person is 70 kilograms. Their final velocity is 0, minus their initial velocity, which is basically the final velocity of that free fall. Okay, so when they're here, that becomes the initial velocity for the collision. Okay, so minus 77.46. If you don't do that, if you don't do it like that, you're going to end up with 77.46. I will consider that wrong, because it's 0 minus, because your final velocity is 0, not 77.46. And if you do the math here, you should get a force equal negative 10,844.35, enough to kill them. All right? And the negative here, it just means that it's pointing up. It's pointing against the way they are moving. Okay. Let's look at this picture here, which is number 20. The wreck pushes crates starting at rest across the floor for 3 seconds with the net force as shown, right? For each crate, rank the following from greatest to least. Now, change in momentum. Now, since I don't have the velocities, I'm going to have to rely on the change in momentum as being Ft, because change in momentum is Ft. So in here, the change in momentum is force, which is 100. Now for all of them, it's 3 seconds. So it's 100 times 3, so that's 300 kilograms meters per second, or newtons times seconds. This is going to be 75 times 3, which is 225. This one is going to be 50 times 3, which is 150. Okay, so the greatest will be A, and then comes B, and then comes C. Yeah. The final velocity, so for the final velocity, well, the impulse or the change in momentum is m Vf minus Vi, or V initial, I guess. Okay. They all start from rest, so really going to drop this here. So the change in momentum, so this is 300, okay, equals, so basically if you want to find the final velocity, you just do change in momentum over the mass. So this is going to be 300 over 30. This is 225 over 20. And this is 150 over 10. So this should give us a 15. This is going to be 11-ish, 11 point something. And this should be 10. Okay, so the order should be CBA. Okay, and momentum in 3 seconds, you're just going to have to take the final velocity, right, and multiply it by the mass. So that should be ABC, right?
Okay, number 22. Okay, Aiden takes a handoff and runs towards the line of scrimmage. He's met by Big Steve, who applies a force of 250 newtons on Aiden in 0.55 seconds. What impulse acts on Aiden? So the impulse on Aiden is going to have to slow him down, basically, right? So let's take a look. So let's just say Aiden is going, is going right. So this is Aiden. Now Steve hits him with the force to the left. So I think the impulse, if we look at right as positive, the impulse on Aiden has to be negative, okay, because the force is going in the negative direction. So it's 250 times 155. In other words, I'm doing J equals Ft. But I have to throw a negative in there because the force is in the opposite direction Aiden is traveling. So if you do the math here, you should get negative 137.5, I think, newtons times second. Yeah. Okay. What is Aiden's change in momentum? Well, change in momentum is the same thing as impulse according to our equations. So that's going to be negative 137.5 newtons times seconds, which means he's going to have to slow down. If Aiden has a mass of 52 kilograms and is brought to rest, what was his initial velocity? Well, let's take a look. So I can say that the change in momentum is m final velocity minus the initial velocity. This is negative 137.5. His mass is 52. His final velocity is 0 minus the initial velocity. Now, if we do the algebra here, we can divide by 52 and then we get VO. So VO should be 2.64 meters per second. Okay. All right, number 23. Mark McGuire stepped out to the plate and hit 150 grams. So you got to be careful with the mass there. fast ball traveling at 30 meters per second. The impact caused the ball to leave the bat with a velocity of 45 meters per second in the opposite direction. So here we're looking at a change of 75 or negative 75, depending on how you look at it. If the impact lasted for 2 thousandths of a second, 2 milliseconds in other words, what force did McGuire exert on the ball? So let's just say the ball is moving this way at 30 meters per second, has a mass of 0.15 kilograms, and the force is in the opposite direction. Okay. All right, so I'm going to write, since I'm looking for force, I'm going to write Ft equals. Now, I do have the two velocities and I have the mass, so I think it makes sense to write m v final minus v initial. So F times T, which is 0.002. You have to be careful. If time is given in milliseconds, you have to change it. Equals 0.15 times, now the final velocity. Okay, so if we look at right as positive, okay, the final velocity would be in the negative direction minus the initial velocity, which is 30. So we already say that there will be a difference of 75. So the force in this case will be in the negative direction, which makes sense that we get a negative number in front of the force. So that's going to be negative 5625 newtons, right? Now let's just say we choose right as positive, and the force will be negative. So this would be, I'm sorry, if we choose right as negative, this will be in the positive direction. So this would be negative 30. So it would be positive 45 as the final, minus negative 30. And this will become positive, which makes sense. But in terms of magnitude, we should get the same number. 24. A 0.144 kilogram baseball is pitched horizontally at 38 meters per second. After it's hit by the bat, it moves at the same speed but in the opposite direction. It's kind of like similar to the previous one. If the bat and the ball were in contact for 180 milliseconds, so you have to be careful with that. So you have to divide that number by 1,000 to get your seconds. What was the average force the ball exerted on the bat exerted on the ball? So we go in at 38. I'm going to look at right as positive. We're leaving with 38, but in the negative direction. So I'm going to say Ft is m v final minus v initial. In other words, the force is in this direction here. So if right is positive, I should end up with a negative number. So F times 0.8 divided by 1,000 equals 0.144 times Vf, which is negative 38, minus the initial velocity, which is 38. And the force will be negative 13,680. If you reverse the directions, you should just get a positive, because this will become positive 38 minus negative 38. Okay. 25. Okay. A car moving at 10 meters per second crashes into a barrier and stops in 0.5 seconds. There is a 20 kilogram child in the car. Assuming that the child's velocity is changed by the same amount as the car's in the same time period, what is the impulse needed to stop the child? Okay. So J equals, well, I can't do the forces, I mean, especially that it's asking me to find force here. So I have to do, J is M delta V, or VF minus the initial. Okay, so that's just going to be 20 kilogram child comes to stop minus the initial velocity is 10. So it's negative 200 newtons times seconds. So it's negative because it's trying to slow him down. Okay, what is the force, the average force on the child? I think we just have to do J equals Ft. Okay, so this is known. We will calculate it earlier. F, and the time is a half a second. So there will be a force of magnitude 400 newtons just going against the child. Sorry, that's why you see a negative. Okay. number 26. A student, 63 kilograms, falls freely from rest and strikes the ground. During the collision with the ground, he comes to a rest in a time of 0.04 seconds, so 400ths of a second. The average force exerted on him by the ground is positive 18,000. So now here we're looking at up as being positive. That's what it looks like. We did a previous problem where down was positive, where the upward direction is taken to be positive. From what height did the student fall? Assuming that the only force acting on him during the collision is that due to the ground. Okay, so let's try. So I'm going to say Ft equals m Vf minus V initial. So what I'm going to try to find here is actually find with what speed they're gonna hit the ground, okay, and work backwards and maybe do kinematics or conservation of energy to find the initial height. So let's try 18,000, okay, times 0.04 equals 63. Now the final velocity is 0 minus the initial velocity. Okay. So if we do the math correctly here, we should get, okay, so 180 times 4 divided by 36. So I get an initial velocity of 20 meters per second. Let me just do that again. Actually, I have the answer here. No, that's not what it is. Oh, I divided by 36. That's 63. Okay, so then that times 36 divided by 60. Yeah, so this is 11, negative 11.43 meters per second. That's in terms of velocity. It just means that they're traveling in the negative direction. So I'm going to do conservation of energy. I think in the answer key on haiku, I have it done with kinematics. Don't need to do that. So they start from a height h, so they have this much gravitational potential energy. When they hit the ground, they're going to have just kinetic energy. That's the velocity that they're going to have. Okay? It's technically the final velocity for the free fall, but the initial velocity for the collision with the ground. Okay, so I don't care about their mass. That was only important here. So this is going to be 10h equals 1/2 times that number squared. And I'm going to leave whatever was in the calculator. So I'm going to square that. In other words, I'm going to leave all the digits. Divided by, okay, and then divided by 10. So it looks like it's 6.53. The height is 6.53 meters. Okay. All right, so let's look at this picture here. So this is going to lead us to, actually I'll do the multiple choice first. A car having a total mass of 2,000 kilograms and traveling at 20 meters per second smashes into a tree. The car is stopped in 0.25 seconds. The driver of the car is not held in place by a seat belt or any other restraining device. Just after impact, but before the driver hits any part of the car, the acceleration of the driver is closest to, well, they're going at a constant speed of 20 meters per second. So there would be like no acceleration, right? And once they hit the tree, there will be some deceleration. Yeah. I'm sorry. Once the driver hits some parts of the car, there is no reason for them to slow down from 20 meters per second because inertia will keep them going, so there will be no acceleration. Once they hit a part of the car, then they'll decelerate, and they will this will happen quickly because the time to stop is pretty short. Okay. All right, this one I'm not going to do. We can do it either in class or you can look at the answer key. All right. This page here, we're going to leave blank. We're going to do some practice in class, or I'll do a video, and you can fill in the blanks. All right, so let's go to some conceptual stuff here. RT1. Identical boxes are all filled with different objects. That are all filled with different objects are initially at rest. A horizontal force is applied for 10 seconds, and the boxes move across the floor. The mass of the box with its content and the net force is given in each figure, right? Rank the magnitude of the change in momentum. Now, if I want to find the change in momentum, technically I need the mass and the change in velocity. I don't have that information, right? But I know that the change in momentum is also equal to impulse, which is Ft. Now I know the force and I know the time, right? Now, the force is applied for 10 seconds in all these cases. So I really don't, in other words, the time is constant. So if I want to compare the change in momentum of all these problems, all I have to do is compare the forces applied to them. So I think the order is going to be D first, then comes A and B tied together for a second place, and C will be last. Okay? All right, so let's look at the next one. Okay. Identical boxes that are filled with different amounts of sand are initially at rest. Same idea. A horizontal force is applied and the boxes move across the floor. The mass of the box with its content, the net force acting on the box while the horizontal force is applied are given. All right. Rank the magnitude of the impulse. Okay. Well, I think this is easier than the other one. So impulse is just going to be F times the amount of time that the force is applied. So here, this is the explanation which you have to write. Time is the same for 2 seconds for all of them. So if I want to compare the impulse, all I have to do is compare the forces. So it's going to be D, then A and B, and then A and B together, and then C last. RT3. Two blocks are released from rest at the same height. Block A slides down a steeper ramp than block B. This looks similar to something we did in the past. Both ramps are frictionless. The blocks reach the same final height indicated by the lower dashed line. Block B weighs more. So I'm going to say this has a mass of big M and this has a small mass. Is the work done by the gravitational force on the block A greater than, less than, or the same as the work done by the gravitational force on block B? Well, the work done by gravity basically is just going to be mg times h. So for this case here, more work is going to be required on block B. So the work done on block A is less than. So the answer is 2. Is the speed of the block of block A greater than, less than, or the same as the speed of block B? Now, if you do conservation of energy, they both start with mgh, okay, and they end up with 1/2 mv squared. And in this equation, we can divide both sides by the mass, which means the mass is not important or plays no role. So they should have the same velocity because they started from the same height. Is the momentum of block A greater than, less than, or the same as the momentum of block B? Well, they both have the same speed, okay? Block A has less mass, so the momentum of block A will be less than. Okay, let me see if there's any other questions. No? Okay. So for B, we say that they're going to have the same speed, so it's 3. All right, RT4, bouncing cart. Change in momentum. So now keep in mind that when you change it, when you bounce in, direction changes, right? So the change in velocity, it's going to be like the sum of the two velocities, technically, right? Okay. So cart with spring plungers run into fixed barriers. The carts are identical but are carrying different loads and so have different masses. Okay. The velocity of each car just before and just after impact is given. So when you see these lines behind the car, it means that it's moving to the left. When you see them behind here on this side here, it means that it's moving. Means that it's moving right. Right. The magnitude of the change in momentum. Okay. So the change in momentum equals m vf minus the initial. Right. Now they have different masses. So okay. So we're gonna have to do m times that difference. And since we're looking for magnitude, we could care less about the sign. So the mass here is 10, and there is a change of 6. Whether 6 or negative 6 depends on how you look at it. Because you're going at negative 3, your final velocity, let's just say left is, well, here they're actually telling us that left is negative, right? And right is positive because they're making this positive. So it's 3, which is the final, minus negative 3. So that's a positive 6. So this is, change in momentum is 60. For B, it just comes to a stop. So the final velocity is 0 minus negative 2 times 20. So this should be just a 40. Okay. For C, it's 10 times, it's going to the right after the bouncing with 1 meter per second minus the initial, which is negative 1, so that should be just 10. And this one here would be 20 times 1 minus negative 1. Okay, so this should be 20. All right, so the ranking should be A, B, D, and C. Right? A, B, and C. Yep. Okay. That's not what I have here. Oh, this one is 40. That's what it is. 40. Okay, so let's look at it again. It should be A, then B and D are tied together, and C comes last. Okay. RT5. 2 skaters pushing off each other. Okay, so we're going to probably think about try to figure out information about the force. 2 skaters, a large girl and a small boy, are initially standing face to face. So basically the girl has more mass and the boy has a smaller mass. After they are no longer touching, the boy has more kinetic energy than the girl. A physics student who is watching makes the following contention about forces that the boy and girl exerted on each other. Since the boy has more kinetic energy, he also has more momentum. So the girl had to have pushed harder on him than he pushed on her. Well, that's not true because according to Newton's third law, they must have the same force must be acting on them. Okay? Yeah. Another way we could look at it, we can say, well, when they were at rest, they started with 0 momentum, total momentum, right? Now, when they push off each other, they have to have the same magnitude of momentum, but just in opposite directions. So the momentum of the girl has to be equal to the momentum of the boy, but with a minus, I guess, right? But in terms of magnitude, it's the same. Okay? Now, which means that change in momentum was the same, right? Change in momentum was the same. And we can also actually talk about that in the sense that change in momentum is Ft. Now this F is external, right? So while they were pushing off each other, okay, the force was internal. So technically there was no change in momentum of the whole system, right? So to get us to here, but it's the same thing. So since the momentum is the same, right, and the change in momentum, okay, change in momentum is F times T, okay? Now, they have the same change in momentum because they went from 0 to some amount of momentum that's equal to both of them. The time of the push was the same for both of them, so the force had to be the same. But I think it's easier to explain it with Newton's third law. It's much quicker. Okay. Okay. Two boxes on a frictionless surface, momentum and speed. Two boxes are tied together by string and are sitting at rest on a frictionless surface. Between the two boxes is a massless compressed spring. The string tying the two boxes together is cut and the spring expands, pushing the boxes apart. The box on the left has 4 times the mass of the box on the right. After the string is cut and the boxes lose contact with the spring, with the magnitude of the momentum of the box greater, less than, or equal to. Okay. All right. We can look at this in terms of the conservation of momentum. Okay. So these two here combined started with no momentum. Okay. After this split, the 4m will have momentum. So I guess I call it 4p, 4m, plus the momentum of the m. So the momentum of each would be equal. Their momenta would be equal, except that they would be in opposite directions. Okay. All right. So they're going to have the same. It's going to be equal. It's going to be the same, right? At the instant after the string is cut, that the boxes lose contact with the spring, will the speed of the box on the left be greater than, less than, or? All right. So momentum is m times v. Since the momentum is the same, the one with the less mass will have to go faster. So the one on the left will have to go slower. So it has to be less.